For the next part of today's lecture, we're going to be talking about blood pH. So it's really important that we maintain blood pH within a very, very narrow range, between 7.34 and 7.38. If it falls below that, we go into acidosis. Above that, we go into alkalosis. And below 7 or above 7.8, we die. It's a very, very narrow range. So we have a bunch of systems that are going to help us maintain that. Now, the biggest one is simply the bicarbonate buffer. This is bicarbonate going back and forth between bicarbonate, carbon dioxide, carbonic acid. And this back and forth allows us to have that buffering effect. You remember buffering from that very first lab, when we were still able to do labs. So you have this buffering effect. And this is going to mean that it takes a lot more to affect the pH. Mostly the pH is pretty well maintained just by this buffering effect alone. So what could be a larger change is actually going to be moderated and have a small effect because of this buffering system. And their bicarbonate is moving back and forth among these the extracellular fluid compartments, so it moves between plasma and the interstitial fluid. It doesn't go directly into the intracellular fluid. To move to the intercellular fluid and back, it has to be transported as carbon dioxide. However, because it's so easily converted, some of it will be converted to carbon dioxide, which can go right through the plasma membrane and go back and forth. So we'll have this flow back and forth between, with some of it being carbon dioxide, some of it being the bicarbonate, and some of it being the carbonic acid forms. Now, again, we need to maintain this pH regulation. We need to maintain this pH regulation very tightly. So to do that, we have two methods of adjusting the pH in the body. The main one is respiratory pH regulation. Our main response, our first sort of hair trigger, first initial response to a change in pH is changing our breathing patterns. Because remember, an increase in CO2 is going to decrease pH and vice versa. So if our pH drops, we will increase breathing, and that will decrease the CO2 level and bring us back into homeostasis. So this is a response most of the time to pH specifically, to this change in blood pH. And that change in blood pH causes this increase in breathing, decrease in CO2. On the other hand, if we have an increase in pH, then we will slow our breathing, and that will allow us to increase the CO2 and bring the pH back down. Now, that's great for sort of the short term, but obviously there are some problems with that because CO2 isn't the only thing we need to control with breathing. We also need to control oxygen. And so if our only response to change in blood pH is breathing changes, well, then we start to run into a problem. So we have a sort of a slower, longer term pH maintenance where we can modify this in the kidneys. So in the kidneys, we can affect the amount of H+ that goes out in the urine and the amount of bicarbonate, which on its own is a base, that goes out in the urine. So in high pH environments, we will let a lot more bicarbonate go out in the urine. It's just filtered out normally, but under normal conditions, we reabsorb most of it. If the pH is high, we'll reabsorb less of it. H+ not only filters out, but under low pH conditions, we can actually excrete extra. So we can secrete protons, secrete these hydrogen ions, and get rid of more, as well as reabsorbing all the bicarbonate or almost all the bicarbonate. And that allows us to decrease the pH of our urine, which will increase the pH of our blood. So if blood pH is high, then we want to produce high pH urine, decreasing the pH of our blood. If blood pH is low, we want to produce low pH urine, increasing the pH of our blood. So looking at this in a little more detail here, we have our secretion of H+ ions from these cells, from our proximal tubule cells, which will create our carbonic and our bicarbonate, and create carbonic anhydrase, which we can reabsorb as CO2, and we can actively move the bicarbonate back into the bloodstream. So this is looking at a low pH condition. We're going to actively secrete H+, creating this free bicarbonate that's going to go back into the bloodstream. And obviously, we're reabsorbing this bicarbonate, but if we reabsorb less of the bicarbonate, then that's going to change it as well. Now, this acid-base balance that we're maintaining with the respiratory and the renal system is really important here. And this is where we can look at what happens if it goes wrong. Now you'll see here we have symptoms of acidosis and symptoms of alkalosis. Now, acidosis, you're going to see headaches, sleepiness, confusion, loss of consciousness. Now, what's important here is if you look at alkalosis, you're going to see confusion, lightheadedness, coma. So you're noticing there's some overlap, and that's where things get complicated. Again, with the digestive system, you're going to see nausea and vomiting in both versions. And this can be an issue, that it's not necessarily always easy to tell what's going on here. We can talk about the different types of alkalosis and acidosis. So we can talk about metabolic and respiratory. So in this case, we're looking at metabolic alkalosis. So alkalosis, we're raising the pH. This is generally caused by, usually by problems in the digestive system. Severe vomiting can cause this because you're losing a lot of stomach acid. And that loss causes your body to need to produce more stomach acid, and that pulls H+ ions out of the blood, resulting in alkalosis. So people will breathe less, which results in low oxygen levels, tend to have confusion, restlessness, and lethargy. This can also result in nausea and vomiting, so making that problem worse. And we can also see this from diuretics. People who are taking high levels of diuretics, sometimes they're just losing too much acid in the urine, and so that can result in metabolic alkalosis. Metabolic acidosis, on the other hand, is when the blood is too acidic. This can happen because there's excessive hydrogen ion production because of metabolism. It can result from a failure to eliminate the hydrogen ions, for renal failure. Can result from dehydration, where you're not producing enough bicarbonate. Or it can result from diarrhea, where you're just losing too much bicarbonate to that diarrhea. And this is going to result in hyperventilation. You're going to be breathing a lot to try and get rid of that acid, even though it's not, of course, CO2 that's the problem. It's going to result in headaches, drop in blood pressure, and again, nausea and vomiting. So this is what we're going to see with acidosis. Now, in addition to these metabolic types, you can also have respiratory alkalosis and respiratory acidosis. So respiratory alkalosis is what happens when people hyperventilate. So when people become very anxious, sometimes they start breathing too fast, they feel like they're not getting enough oxygen, And so they overbreathe in response to this, and that actually causes them to eliminate too much carbon dioxide, causing alkalosis from breathing. This can result in nausea and vomiting, lightheadedness. In extreme situations, it can result in seizures. However, the likely endpoint of this, if it's hyperventilation, is passing out. If somebody passes out, their breathing goes back to normal, and this sort of solves itself. Now, you've probably heard things about like breathing into a paper bag. Technically, that can help because it recirculates the carbon dioxide. However, these days it's not generally advised because the truth is it's actually really, really hard to tell someone who is hyperventilating from someone who is actually not getting enough oxygen. And so unless you're really sure, we're really cautious about that. Usually the better options are just like try and calm the person down, let them relax, those sorts of situations. Now, respiratory acidosis happens when someone isn't able to get rid of the carbon dioxide. So this can happen if there's some sort of airway obstruction or alveolar disruption, like pneumonia. Obviously, when we're talking about COVID, this is something that we're seeing. So that pneumonia where the lungs are filling up with fluid, that results in this respiratory acidosis where they can't get rid of the carbon dioxide. And that's just as big a problem as not being able to get the oxygen. This is going to result in headache, drowsiness, disorientation. It results in a drop in blood pressure. And this, in fact, can be sort of one of the big issues that leads to problems for people with pneumonia just as much as that lack of oxygen. All right, and then this brings us back to the regulation of ventilation, which I've talked about before, but again, we're back to a lot of this is regulated through pH, so that decrease in pH is caused by CO2, which then increases breathing, and vice versa. So you're going to see this ventilation regulation a lot through pH, and that's going to allow us to, in turn, regulate the pH. Now, there are some interesting edge cases that can happen. If you're in a low oxygen environment, pH and oxygen may be separate indicators. So if you're in, for example, a high altitude, low oxygen environment, you may be getting rid of CO2 very effectively, but still not getting enough oxygen. And on the other hand, you can have cases where CO2 builds up, but you are getting enough oxygen. In which case you are going to breathe more rapidly to get rid of that CO2. That just results in excess oxygen. That's not a problem in the short term. Oxygen does have cancer-causing issues, not what you think about. But in general, in the short term, excess CO2 buildup just causes you to breathe more, not really causing a problem because you're pretty close to your maximum oxygen capacity to begin with. So this is all of these pieces. Now, I want to remind you that we have this review activity. So this review activity is putting all of these pieces that we've been talking about, everything that we put here all together, and drawing a diagram to put all these pieces together. So we're going to do a diagram for blood pressure, a diagram for pH, and a diagram for oxygenation. Now, you can do these individually or as a group, but what I want you to be aware of is that this is not a simple task. When I'm assigning this to you, I'm assigning this as a full application activity. Expect that drawing these 3 diagrams is going to take just as long as a POGIL or a case study if you're doing it right, because there's a lot of pieces to put together. The renal and the cardiovascular and the endocrine and the respiratory systems effects on all of these things. So you think about what affects blood pressure, what affects those things that affect blood pressure. Do the whole cycle. This is posted on Blackboard. So put that together. You can submit it either as a computer drawing or as a picture of a hand drawing. You know how to find me. If there are any questions, please come to my Zoom hours or send me an email. All right.